Hi class, in this video lecture here what we want to talk about is a differentiation method called implicit differentiation. And so what we're going to be doing in this section here is the first thing we're going to talk about is how you distinguish between functions written in what we call implicit form and explicit form. And you'll see the subtle difference, and explicit form, I'll give you a little preview for it. That's just something like y is equal to 2x squared plus 5, right? Where y is, solved for just the other variable. Implicit form's a little bit more difficult, right? And this is what's going to lead us into what's called implicit differentiation. That's what this section's about. So then the next thing we'll do is we'll talk about how you use implicit differentiation to find the derivative of a function. And these two topics here will be this lecture right here. And then what I'm going to do is expand on this topic by talking about how you find the derivatives of functions using what's called logarithmic differentiation. And this right here will be in the second video lecture. So I'm going to split this lecture up into two videos. Okay. So first off, let's talk about the difference between implicit form and explicit form. So in an explicit relationship, one variable is defined completely in terms of the other. So it's something like this. That y is equal to exactly what I had back here, 2x squared plus 5. You can solve y or x in terms of the other variable, or even something like this, right? It can even look like this. X is equal to 3y cubed minus 7y. As long as you have one variable solved in terms of the other one. Now, what's slightly different here is this thing called an implicit relationship. Okay, so an implicit relationship is a relationship which relates the variables involved. So it's some type of equation that involves both variables. Now, often, not every time, but often you cannot solve for one variable in terms of the other variable when you have an implicit relationship. Like, let me show you this one. Maybe something that looks like this. Something like x squared plus xy plus y squared is equal to 9. Like, there's a relationship that exists between the variables x and y. It's defined by this equation, x squared plus xy plus y squared is equal to 9. But the problem is you can't solve for one of the variables in terms of the other, okay? So, how would you find dy dx for this relationship? And that's what we're going to talk about in this section here. All right, or it can even look something crazy like this, like the square root of 2xy minus cotangent of x squared y squared is equal to x plus y. I don't know, just something crazy like this, okay? And what I'm going to do and show you in this section is how to find dy dx for that relationship. And what you're going to notice here when we do is that dy dx is actually going to involve both the x and y variable. And you'll see that. Okay, so explicit forms, you got the variable solved for the other variable, and implicit forms for the ones we're going to look at, you just can't solve for one of the variables, okay? So one of the ways I like to introduce this topic is just consider this equation, okay? This is x squared plus y squared is equal to 1. All right, literally this is just, this is a circle with center 0, 0 and radius 1. All right, so it just looks like this. This is gonna be a terrible circle, really small here. Okay, but it looks like that. This is my x squared plus y squared is equal to 1. And what I want to do here is I want to find the slope of the tangent line at the point 0, 1. Now you can actually just like look at it and see that it's going to be a horizontal tangent line. But even regardless, how did we do this, right? We found the slope of the tangent line by finding the derivative. Okay, in this case, dy dx. All right, but how do we do that for this equation here? Right, like if you were to try to solve for y, right, you would get something weird. You would get y is equal to plus or minus the square root of 1 minus x squared. But like, I never talked about how you find the derivative involving this plus minus. And it's like, you know, how would you do it? All right, so that's what we're going to talk about with this implicit differentiation. And this is actually a very, very easy problem here to do. And we'll do it. We'll come back and revisit this in a second. All right, so to be able to do implicit differentiation, so to find dy dx, we differentiate with respect to the x variable. And what you have to recall here, it's really important, you have to recall the chain rule because we use it a lot. All right, so here, look, we'll start with something simple, okay? If I say find the derivative with respect to x of x cubed, do you notice how this x in the bottom of the differentiation expression is the same as the variable? Okay, so the variables agree. You just, the derivative of this very easily should just be 3x squared. But now recall the general power rule. Okay, if I say find the derivative with respect to x of u to the n, okay, this was nu to the n minus 1 times u prime. Okay, so the derivative of u with respect to x. Okay, so another way of saying this is n times u to the n minus 1 times du dx. Okay, because that's what u prime is, it's du dx. So now, okay, if I have this, all right, so now looking at this, let me change instead of x cubed, I say find the derivative with respect to x of y cubed. Okay, notice here the variables do not agree. Okay, variables disagree. So here you're going to need to use this general power rule, which is really kind of like the chain rule. Okay. So look, instead of u, okay, it's just y because the variables disagree. So you're going to just bring the 3 down. So this will be 3y squared. And whenever the variables disagree, you need y prime. But what is y prime? Y prime is dy dx. Okay, and hopefully you can see what's going on here. We're trying to find dy dx in our equations. All right, so whenever you differentiate with respect to x of anything with a y, you're going to differentiate it as normal. That's what the general power rule says here. Okay, and then you're going to tack on this dy dx. Like, let's take a look at this one. Let's differentiate with respect to x. Let's look at 5x squared plus 2y squared. Okay, so look, you're going to differentiate the 5x squared first. The 2 comes down, that just becomes 10x, plus. Now when I'm differentiating with respect to x, look, I'm differentiating y, so the variables disagree. So 2 times 2 becomes 4. This becomes not y squared, but y. And then whenever you differentiate the y variable, you're going to tack on a dy dx. And it's the same thing here. If I ask you to involve, like, let's just consider something with the product rule. X squared, y squared. All right, so I'm telling you to differentiate with respect to this. So you start with the first part, x squared. The derivative of that is 2x times y squared plus, now x squared. Now when you go to differentiate the y squared, the 2 comes down, the y becomes y to the first power, but then I differentiated with respect to x, so you're going to tack on this dy dx. So whenever, really important, whenever you're differentiating the y, okay, differentiate it using the general power rule, and instead of writing this, y prime, it's just this dy dx, this just dy dx. Okay, so now let's revisit, okay, the circle problem using these guidelines for implicit differentiation. Okay, so here's how you're going to find the goal. The goal with implicit differentiation is to find dy dx. All right, so the first thing you're going to do is you're going to differentiate both sides of the equation with respect to x. Then all you're going to do is you're going to collect all terms involving dy dx, okay? Because remember, when you differentiate a y, you get dy dx on the left side of the equation, and move all other terms, no matter what's in it, as long as it doesn't have a dy dx, to the right side. Then you're going to factor out a dy dx from everything on the left side, and I'll show you how to do this. And then from there, you just solve for dy dx. And it will be a little tricky the first few times you see me do it, but I promise after you see me do it a few times, maybe you have to watch the video again and again or something, but after you see me do a couple examples, and I literally have 1, 2, 3, 4, 5, 6, 7, I have 8, 9 examples picked out here, maybe 8, okay? So we're gonna do it a bunch, so you're gonna get to see a lot here. All right, so let's revisit this, okay? Let's consider x squared plus y squared is equal to 1. All right? So it's just this circle, okay? This x squared plus y squared is equal to 1. Let's find the slope of the tangent line at the point 0, 1, okay? So you need to find dy dx. Okay, so the first thing you're going to do is you're going to differentiate both sides of the equation with respect to x. So I'm going to differentiate with respect to x, both sides. X squared plus y squared, and this derivative with respect to x of 1. Now look, we've looked at basically almost here x squared plus y squared. There's some constants in front. So now, okay, you're going to complete the differentiation. So the derivative with respect to x of x squared is 2x plus, now when I differentiate here y squared, I get 2y, and then remember you get dy dx. All right, and that's going to be equal to 0. All right, because when you differentiate a constant, it's 0. So look, keep everything with the dy dx on the left side and move everything else to the right side. So I'm just going to subtract the 2x over. So these are gone, and I'm left with 2y dy dx is equal to minus 2x. Here I don't need to factor out dy dx because there's only one term. So to solve for dy dx here, I'm literally just going to divide both sides by 2y. And look what happens when I do. 2y cancels here. And look, I'm left with dy dx is equal to, the 2's are going to cancel, negative x over y. All right, so in this case here, whenever you do implicit differentiation, your dy dx will involve both variables, okay? And that's okay, and that's literally okay. Because remember, these type of equations, we just can't solve for one variable. Okay, so it would make sense then that our derivative would contain both variables. Now to find the slope of the tangent line, plug in 0, 1 into dy dx. So I write it like this. I go dy dx, and I put this line here that tells me to evaluate it at 0, 1 is equal to, so I'm plugging in 0 for x, so minus 0 over y, when in this case is 1. So the slope is 0, which is what we would expect because the point 0, 1, we have a horizontal tangent line. Okay, we got it. All right, now let's just practice it. Okay, let's literally do a bunch of examples just so you can continue to see the process. All right. All right, so for these ones here, let's find dy dx for the following. So we'll do this first one here. let's look at 2x cubed plus 3y squared is equal to 64. Okay, so we're going to differentiate with respect to x both sides. All right, so let's go through. Bring the 3 down, so this becomes 6x squared plus, bring the 2 down, right? 6y, and then it's y to the first power. Okay, but then remember, you differentiated y, so you get dy dx is equal to, here, well, the derivative of a constant is 0. So subtract the 6x squared over, so you get 6y dy dx is equal to negative 6x squared. And then divide both sides by 6y, and you get dy dx is equal to negative 6x squared divided by 6y. Again, the 6's cancel. Dy dx is equal to negative x squared over y. Okay, pretty straightforward. All right, this one looks a lot like, the circle example. So let's mix it up now. Okay, let's find dy dx for the following here. Okay, let's look at x cubed y cubed minus 4y is equal to 2x. Okay, so to find dy dx, differentiate both sides with respect to x. All right, notice here you're going to need to use the product rule, okay? Because I have x cubed times y cubed. So the derivative of x cubed becomes 3x squared times y cubed minus, now the plus the x cubed. Now when I differentiate y cubed, I get 3y squared, but dy dx minus. Well, here, if this was an x, the derivative would just be 4. So it's minus 4, but I differentiated y, so dy dx is equal to, now the derivative with respect to x of 2x is just 2. So look, I've got 2 terms with the dy dx. So I'm going to take this 3x squared y cubed, and subtract it over. Okay, now notice here, factor out the dy dx on the left side of the equation. Do you notice how they both have a dy dx? I'm going to factor that out. So dy dx times 3x cubed y squared minus 4 is equal to 2 minus 3x squared y cubed. Now look, to solve for dy dx, you're literally just going to take this and divide it over. So you get dy dx is equal to, so this part here, 2 minus 3x squared y cubed divided by, now this, because we divided this over, 3x cubed y squared minus 4. So you can see these parts are a little bit more tricky, right? Like there's definitely a lot going on here, right? There's a lot going on here. So you have to be very, very meticulous as you work through these. Okay, let's do an even harder one, right? So let's try to find dy dx for this. Let's look at the square root of xy is equal to x squared y plus 1. Okay, so you're going to differentiate with respect to x. I'm going to rewrite this as xy to the 1/2 power, okay, because that'll help me. And differentiate with respect to x of this. Okay, so here's where it gets really, really confusing. All right, you need to chain rule this, okay? because you have a chain rule and then you have a product in here, okay? So you're going to bring down the 1/2. So 1/2 x comma xy, excuse me. 1/2 minus 1 is the minus 1/2 power times, now this is where it gets weird, okay? You have to product rule this. So the derivative of x is 1, so you have 1 times y, which is just y, plus x, and then the derivative of y is dy dx. Yeesh, a lot going on. Is equal to, here you need to, you need to do the product rule again. So this becomes 2xy plus, now x squared, and then the derivative of y is dy dx, and then the derivative of 0, or derivative of 1, excuse me, is 0. All right, so here's where it gets confusing. So I'm going to distribute this, but I'm going to move this as a square root in the denominator. So this is y over 2 square roots of xy plus x over 2 square roots of xy dy dx is equal to 2xy plus x squared dy dx. Okay, so I'm going to move this over. I'm going to move the dy dx over. So I'm going to move this over here, and then I'm going to subtract this over here. So look, I have this part here. So I have x over 2 square roots of xy dy dx minus x squared dy dx is equal to, now I have this, 2xy minus this. So minus y over 2 square roots of xy. I know a lot going on here. So factor out the dy dx. So dy dx. And then over here, I have x over 2 square roots of xy minus x squared is equal to 2xy minus y over 2xy. So a lot going on here, okay? So then from here, I know, got to divide this over. So dy dx is equal to this 2xy minus y over 2 square roots of xy divided by all of this. X divided by 2 square roots of xy minus x squared. So from here you could simplify it, right? Like you could get everything under a, if you could get everything under 2 square roots of xy. So what you could do is you could just multiply this by 2 square roots of xy divided by 2 square roots of xy. And then you would get dy dx is equal to this times this. So this would be 2, or 2 times 2, excuse me, is 4. Xy times square root of xy would be xy. This would be 1 1/2 to the 3/2 power. Here it would cancel out minus y divided by, when I distribute, here it would cancel out x minus x squared times the square root of xy. So, you know, the algebra of even of cleaning this up is very difficult. It can be challenging. So there's a lot going on with all of these, and I hope you can see, you know, why you have to be incredibly meticulous, because even one little mistake is going to throw this whole thing off. Okay, let's do another one. All right, something just slightly different, but still using implicit differentiation. And it'll be this. Find the equation of the tangent line to this here, this x squared plus xy plus y squared is equal to 9, okay? At the point 3, 0. okay? All right, so we want to find the equation of the tangent line. Okay, so to find the equation of the tangent line, you need the slope of the tangent line, okay? And so to find slope, right, you need to find, of this, you need to find the derivative. So you're going to find dy dx here. So you're going to differentiate with respect to x both sides, right? So look, the derivative with respect to x of x squared is 2x plus, here you're going to need to use the product rule. So the derivative of x is 1, so you get 1 times y is y, plus x, and then the derivative of y with respect to x is dy dx, and then the derivative of y squared is plus 2y dy dx is equal to 0 here, right? Because the derivative constant is 0. So let's subtract this over to the other side. So I get x dy dx plus 2y dy dx is equal to negative 2x minus y. Factor out a dy dx. So the derivative dy dx is equal to negative 2x minus y divided by x plus 2y. So to find the slope of the tangent line, you're just going to evaluate this at the point 3, 0. So slope is equal to dy dx evaluated at 3, 0. So 3 is my x, 0 is my y. So this is minus 2 times 3 minus 0 divided by, and then x, this is 3 plus 2 times 0. Well, what does this get you? This just gets you minus 6 over 3, which is equal to negative 2. So then now just use point slope. So y minus y1 is equal to m times x minus x1. So my point is 3, 0. So y minus 0 is equal to minus 2 times x minus 3, or y is equal to minus 2x plus 6, which is what we got. So again, you just had to use implicit differentiation to find dy dx here, okay? All right, let's do some implicit differentiation involving trig functions, okay? Because those are always fun. All right, so let's do this. Let's find dy dx for, let's look at sine of x plus 2 cosine of 2y is equal to x. Okay, so again, you're going to differentiate both sides with respect to x. Okay, so we know derivative of sine here, that's cosine of x, plus. Now here you're going to need to use the chain rule. Got to be careful, okay? So the derivative of cosine, so that becomes minus 2 sine of 2y. And now look, when you differentiate, you got to differentiate the inside part. So when you differentiate 2y, what do you get? You get 2 dy dx is equal to, and then this derivative of x is just 1. So look, this is cosine of x, 2 times 2, so minus 4 sine of 2y, and then you have dy dx is equal to 1. Subtract the cosine over, you get minus 4 sine of 2y is equal to 1 minus cosine of x. And I forgot the dy dx in there, sorry. And then just divide this over. So dy dx is equal to 1 minus cosine of x all over minus 4 sine of 2y. And look, the negative in the denominator is weird, so I'm going to bring it up into the numerator, but when I do, it's going to make this negative and this positive. So it becomes cosine of x minus 1 all over 4 sine of 2y. So just remember, when you differentiate, you got to differentiate the inside. You got to differentiate the inside of the trig functions here. All right, let's try this one. Let's find dy dx for, let's look at y plus 2x is equal to sine of xy. So again, differentiate both sides. With respect to x. So derivative of y, this just becomes dy dx plus 2 is equal to, okay, take the derivative of the outside. Derivative of sine is cosine of x times y times, now you got to differentiate the inside, xy. So you got to do the product rule. So derivative of x is 1, so that's just y, plus x times dy dx. Because when you differentiate y, you get dy dx. So this is dy dx plus 2. Got to distribute here, is equal to y times cosine of xy plus x times cosine of xy dy dx. So I'm going to subtract this over and then subtract the 2 over. So I have dy dx minus this. So minus x cosine of xy dy dx is equal to y cosine of xy minus 2. Factor out a dy dx. You're left with 1 minus x cosine of xy is equal to y cosine of xy minus 2. And then look, you just divide this over to get dy dx. So dy dx is equal to this, which is y cosine of xy minus 2 divided by this part here. This is 1 minus x cosine of xy. So again, a lot going on. A lot going on here. And you just got to remember, whenever you differentiate y, you get that dy dx. Okay, let's look at now. Let's look at this one. Let's look at find dy dx for, let's look at e to the xy is equal to 5. All right, I'll even make it e to the xy squared, make it more fun. Okay, so dy dx, you're going to take you're going to differentiate both sides with respect to x. E to the xy squared, differentiate with respect to x of 5. Okay, so you're going to have to chain rule this. This is a chain rule then followed by a product rule. So the derivative of e, so you get e to the xy squared times, now you need to product rule this, right? Derivative of x is 1, so you get y squared plus x, derivative of y squared becomes 2y dy dx, and this is just 0. Well, look, distribute. So you get y squared e to the xy squared plus 2xy e to the xy squared dy dx is equal to 0. So you're going to subtract this over. So you get 2xy e to the xy squared dy dx is equal to minus y squared e to the xy squared. Now look, check this out. Check what's going to happen. You're going to divide this over. So you get dy dx is equal to minus y squared e to the xy squared divided by 2xy e to the xy squared. Well, what cancels? E to the xy and a y. You're literally just left with minus y over 2x, which is wild. Very, very wild here when you think about it. All right. We've done some trig. We've done e. Let's do one final one with the natural log. Okay, so last example. Let's find dy dx for the natural log of xy, okay, plus 5x is equal to 12. Okay, so the derivative with respect to x, you're going to differentiate both sides. The natural log of xy plus 5x is equal to the derivative with respect to x of 12. Well, that's convenient. That goes away. Okay. Recall, when you have the derivative with respect to x of the natural log of u, remember what this is. This is just u prime over u. Okay? So u prime here, okay, you're going to have to product rule this again, right? So this is y, we've done this a bunch, y plus x dy dx all over whatever's inside u, x, y. Plus, and then here I have 5 is equal to 0. So to solve this, what you're actually going to do, check this out, you're going to split this up. So you have y over xy plus x over xy dy dx. I'm just going to move this over to start, minus 5. So what's going to cancel here, right? The y's. So you're going to be left with 1 over x plus, and then here you have 1 over y dy dx is equal to minus 5. So I'm going to subtract the 1 over x over. So I have 1 over y times dy dx is equal to minus 5 minus 1 over x. So I'm just going to combine these. So this is 1 over y times dy dx is equal to minus 5x minus 1 over x. And then instead of dividing by 1 over y, you're going to multiply by just y. So you get dy dx is equal to, you could distribute it, right? So you could go times y times y. You literally have minus 5xy minus y all over x. So again, you just have to be meticulous. Okay, there's a lot going on in every single one of these problems. So just, take your time, and very, very much just take your time and be meticulous, and you'll come to the right answers. So I'm gonna split this lecture up, and I'm gonna do logarithmic differentiation in the next lecture.